Hi, my name is Zhaoyan. I'm from Texas A&M University. This is a cooperative work with Jialong Zhang and Professor Guofei from Texas A&M University, and also Professor Zhiqiang from University of Texas, Dallas. Our paper is called GoldenEye. Hope James Bond like that. GoldenEye, efficiently and effectively unveiling malware's target environments. So in this talk, I will follow these agendas to talk about the motivation, system overview, and detailed design of our system. And I will present some evaluation results and then conclude our papers. And I will leave some time for your questions. So let's get started. So the motivation of the GoldenEye is the recent trends in the malware attacks. So we all know the terms target malware. So what is target malware? Target malware is a malware that target on certain high-value victims. And the victims including governments, military, education, civil society networks, and even the Fortune 500 companies. So every people knows that target malware is very malicious. And some representative example is the Stuxnet. So all these reports are reflecting the Stuxnet. And you know Stuxnet, what the Stuxnet did, right? They disrupted the Iran nuclear infrastructures. So the challenge here is we cannot passively to wait and to detect such kind of malware. So our question and the motivation from this target malware is how the target malware decides their target. So we do some research and find there are several ways. The first common way is the identification through some zero-day exploits of the software vulnerabilities. That's what Stuxnet did to explore the Siemens PLC devices. And the second approach, which is more common, is they identify through environment check logic, which we also call such kind of a malware that embed such kind of environment check logic as an environment-sensitive malware. So we conduct an experiment to verify whether common malwares inject such kind of environment detection logic inside of malware or not. And we find, like in our test batch, we have over 1,000 malware samples, and 85% of the malware samples has embedded such kind of detection logics. To be more specific, what we do is we hooking a lot of Windows API calls, and then we think all these API calls were related to the environment detection. For example, like Open Mutex is a common like system calls or API calls to query whether some mutex exists in the system or not. And then we record all their returns and to see whether these returns will deviate the malware's execution or not. So if it's deviate the malware execution, we think that the malware will behave differently in different environments. And this what comes out of the number, like 85% of malware samples have such kind of logic. So based on our study, we will propose our problem. So it's environment-sensitive malware analysis. What that means? So given a malware binary, we want to determine whether it's sensitive to its running environment or not. This is the first question we want to answer. The second question we want to answer is to decide what environment element it depends on. It's a mutex in the system, or a window is displaying in the desktop, or a process is running. What exactly is the environment what affects the malware's executions? The last one is decide what are the malware's behavior difference in a target environment and a non-target environments. So after we propose our problems and want to study on that, we think we are not the first one to work on such topics. There are a lot of related work to detect that, but to detect and analyze such kind of malware, but we summarize there are two main lines of work related to our work. The first approach is we call the enforced multi-path execution paths using dynamic analysis. So there are the two representative work which is published on the Security and Privacy 2007 and the RAID 2007. And the main idea of them is they try to enforce the malware to execute different passes inside of their logic and to determine whether they have different behaviors in different passes. So the advantage of that is also very obvious. Like even because you can enforce the malware to execute any kind of passes you want, you can have a very accurate result to say what kind of the behavior of a malware. And also, you have a high coverage because in theory, you can actually cover all the execution passes as you want. But this approach has a kind of limitation is when you analyze one pass of the malware, when you want to switch to another one, you have to roll back, which means you have to go back to the original deviated point and execute another pass after that. So this will cause the limitation, which is time and resource consuming, which means that every time you want to analyze a new pass, you have to roll back again, recover the snapshots, and start running another pass. It definitely will cost a lot of overhead in this procedure. The second line of approach we think is related to our work is configure multiple environments in advance. So there's a related work published on the RAID 2011. So the main idea is that we configure a lot of different environments in advance and let the malware to run in each of the environments to see whether they have different behaviors or not. So this is definitely a very clever idea, but the problem of, because it's a very lightweight, and actually you can run a lot of malware at the same time, but they are not accurate because you don't know what environment elements you need to configure in advance. So based on the study of these two approaches, we want to propose our approach to do a better work. So this is our proposal, GoldenEye. What is GoldenEye? GoldenEye first is a dynamic malware analysis system, which means that we do not do the static analysis. So as we all know, the static analysis has a lot of limitations, especially analyzing the malware. So the GoldenEye is a pure dynamic malware analysis system. The second, you can efficiently discover the malware's target environment, which means he can find which environment elements that the malware depends on in a very, very efficient way. And also, it can effectively expose the malware's sensitive behaviors, which means you can find what the malware behaviors, what is the malware's target or intended behaviors in these environments. So next, we overview our system. So the design of the GoldenEye is starting with analyze a bunch of the malware samples. And we first is doing the normal procedure of the dynamic analysis. First, we use some monitoring tools to monitor the malware's execution. And we have baseline environments, which we call the baseline and analysis environments. And we do some concrete execution on this malware. And then we get some result. This is the baseline running. But alternatively, we just use a baseline. We can use two environments, but this environment is dynamically generated. And we do not do concrete execution on this alternative environment. Instead, we use the technique we propose called the speculative execution. It's different from the computer architecture speculative execution, but we use these techniques to speculative execute the malware instead of concrete execute them. And then we get a different result, different malware result in different dynamically generated environments. And then we select which one should be the environment to analyze this malware. After we find the suitable environments, we want to deploy this environment online, go back to our baseline and analysis environments, and continue to analyze the malware. So this will be this will be formed as a loop and continually to analyze the malware in this way. So probably you will have a lot of questions about how the system works. Let's introduce some details about the things. The first thing is because as I introduced, we want to dynamically construct the environments of the malware. So the first important part is we want to find when the malware wants to detect its running environments. So we use several ways to detect because we think the malwares use instructions to detect its running environments. So the first way we do is we hook a lot of environment query APIs. Some example is like the open mutex, as I introduced before. And the second way is we find a lot of instructions can use to query the environment informations. Like the CPU ID is a very famous one to query the time and the CPU frequency. And also, we find that there's a lot of environment-related parameters of different APIs. If you import these parameters, you can also use the specific API to query the environment informations, like a get system configure EX. And also, there's a lot of like well-known exploit interface functions, like coin initial instance. So all these things can be used by the malware to detect its running environments. So what we do is we hook all these kind of instructions and the system call and the library calls, and then we can capture the same time that the malware want to query the environments. So after we find the malware's attempt of a querying environment, what do? We want to initialize the alternative environments for each instructions and the API returns. So what we do is we want to, in advance, we label all these environment-related parameters, and we want to consider what will be the possible returns for each environment queries. So if they have n possible returns, we can generate n possible different environments. So this is what I mean by dynamically generate the environments. So let's do a quick example to help you to understand how the things works here. So for example, if the malware call system calls like the open mutex, we will construct two environments. Because we check the open mutex, it will return two possible returns. The first is the object handle, which directly points to the mutex that the malware want to open. So in this way, in this environment, which means if it's returned the valid values, we will say like in this environment, the mutex exists. In another alternative environment, we'll say they will return -1, which means there are no mutex exist in this environment. So in this way, when we capture the malware's query and we construct two alternative environments, what we do in these two alternative environments, we want to do the execution. The execution is based on the tainted analysis. Basically, when one call occurred, we taint the labeled parameters and initialize the environments as the new running index. For example, in the previous example, one context is EAX equals to 1, and another context EAX equals to 0, and we start tainted analysis. So the tainted analysis here, we use a different techniques which we call the speculative execution. Speculative execution is for each instructions, we simulate the execution in all alternative environments. So this is the following example of our previous one. So for example, if the malware do call open mutex, and in our current environment, which is this mutex exists. So in this environment, the EAX will equals to this number. They'll start with FC, these numbers. And in another alternative environment, in this environment, the mutex does not exist. So in this environment, the EAX will equals to -1. So then we taint the output of this EAX and to see whether these tainted instructions will be propagate to another register or memory locations after they execute the following instructions. For example, when they do compare the EX with a 2, we will say in environment first, the ZF will be set to 0, and in another environment, the ZF will set to 1. And this kind of speculative execution stops at a branch point, which means when we reach a branch point, we need to decide which environment we want, which environment we don't want. So this is a graph show how this speculative execution works. So for each line, it's one alternative environments, and we only record the difference part of the different registry. So we use a double linked list to maintain these things, and since we only record the difference of the register and the memory places, we consume very little resources along this execution. So end of the execution, at the end of the executed block, we will have a lot of alternative results and a lot of alternative environments. This one will say we have 4 environments in this branch point. And we see that if we want to go to the left, the environments should follow C and D environments. And if we the left. So if we want to go to the right, the environments should be A and B. So what do? We use our previous work published on the CCS 2012, which is called the branch foreseeing. The high-level idea is like we foresee some code blocks after this branch point, and to see which is the possible branch belongs to the environment that the malware really want to execute it on. So we use several criteria to determine. First is if we find the branching having some termination function, which is not the target branch. For example, if we find there's a branch a system call called exit thread, which means he wants to stop its execution, which we probably think if the malware goes to this branch, it's not desirable. He probably wants to choose another branch. So in this way, we can discard all the environments that lead to this branch. And also, if we find that in one branch they have a lot of malicious functions, we will think this one probably is the malware desired branch. And also, if one branch interacting with the queried environment, which means, for example, if he opens a register, and in this branch, he directly operates on this registry, we will think this is a possible targeted branch or desirable branch. So then we choose this branch will be the malware's desirable branch. After we choose which one is the desired branch, for example, the right one is the desired branch, we continue to discard all the meaningless or useless environments. And then we reach the real malicious things that the malware wanted to do in their environments. But there are also a possible situation we will encounter is like we cannot determine which branch it wants. So that's why we probably can store them into a queue and use this queue to remain executing later. So this is what we propose, a distributed version of GoldenEye. So if we find this branch, we cannot determine that. We can store these informations and to do rollback, recover snapshot, and re-execute this branch later. But we think we will try our best to continue forwards until we cannot do that. So this will save a lot of efforts of loading back and all these things. So next, I will present some of our evaluation results of GoldenEyes. So in our evaluation, we used 2 data sets. The first data set is some general malware and it's over like 1,700 samples, and the second data set is some well-known malware families, including DoQ, Configure, Sality, and iBank. All these things are reported have some environment-sensitive logics, and some of them are targeted malware. So this figure shows how many behaviors we can expose more in different category of the malware. For the general data set, we used the virus total to get the category of each family. So in this example, you can see we can at least expose more than 10% or to 50% of the more APIs in using our ways. And also another thing you probably can see that is some category of the malware behave better than others. For example, the adware and children, they behave better than other things because we think such kind of category of the malware will embed more environment detection logics. So we also compare our GoldenEye with some related work. We compare with the percent of the increased behaviors. So our result is around 46% for the data set, for the first data set. And in the related work one, they can expose like over 55%. And in the second related work, it only can expose like 7%. And also, the number of rolling backs is, our rolling backs only occurs like 123 times. And in the related one, because you need to explore all the things, it's over like 1,400 rolling backs. And in the related, in the second related work, because they statically configure the environments in advance, they don't need to rolling back all the things. And compare with the memory and disk usage, our GoldenEyes consume around like 4 megabytes of the memory along the execution. And we check the papers of related work 1 and 2. We think their memory and disk overage were larger than 5 gigabytes. And we use the data set to detect the malicious behaviors and to see what kind of environment elements they are interested in. For the configure, we find like they interested in some system objects, for example, some registry, and also the network. We find the configure will check their internet connections before they do any malicious things. And also, we find that the malware, the configure will detect whether there is one running process called the explorer.exe. So if there is one exists, he will stop and rename itself and restart the booting. For the thus malware, we find that they detect some hardware, like the USB driver, whether they have USB driver, and also they will detect whether the network connection exists or not. For the Beef Forest, which is a very famous like spyware from China, we find that like this malware will detect some camera, whether this camera has been activated or not. And the Sality, we find that the malware will detect some system information like the keyboard's layout. And then we find that the Sality uses the keyboard's layout to generate some random number for to label itself. And also for the Nitor, we find that they also need to check some network connections before they start the infections. So I will conclude my presentation here. So we propose a novel approach for target malware's environment analysis. And we think our system called GoldenEye, which can effectively and efficiently analyze the malware, the environment-sensitive malware, and expose more behaviors. So, yep, that's all my presentation.
So my question is about the 85% number that you quoted early on in your slides. Where did you get your malware samples from? And did you account for different families of malwares? Because if you don't, it's the case that polymorphic families account for a large number of the malwares.
The data source of our that experiment is from Anubis.
Okay.
And we also collect some of the malwares from the offensive computing. We use a crawler to crawl different types of, because the offensive computing, a lot of them, they have labeling, like tell what category of this malware. So we were evenly distributed different categories. For example, children, adware, and worm, all these things, to try our best to don't have bias of different malware category and the families.
Roughly how many families would you say?
I would say over like 200 different families.
Thank you.
Hi. So I may have missed this, but how hard is it to evade this? For instance, if you're using the contact, the information from the environment as a key to decrypt the rest of your binary, right? Mm-hmm. So you would not be able to reconstruct that.
Yeah, that's a very, very good questions. And to evade our attack, to evade our detections and analysis, there are a lot of ways. Definitely, there are a lot of ways. Like one thing you mentioned is a very, very good point. And to be honest, I don't think we can handle this case. And I would say some like more easy evasion includes like they can just check the environment and do the infection long after that. This is basically our assumption. Why we think our things work is malware will do the malicious things immediately after environment check. Or maybe they will query some environment elements and use them immediately after that. So we can, in this way, we can do it in a very efficient way and to continue analyze them in a very efficient way. But malware can just prevent to doing something like this. For our case, if malware choose to do that, our performance will be very similar to some existing work, like the multipath malware detections and analysis. Does that answer your question?
Right. So I guess if this becomes widely deployed, that's exactly what they will do, right?
Yes. Totally agree.
So you had a slide where you were comparing your results with previous approach, which I suppose are the Anubis-based and the other one by Wilhelm, right? Yeah. So how did you actually do this comparison? Did you re-implement yourself their approach, or did you ask them to compare?
That's also a very good question. For some details, you can refer our paper, but I will introduce some things. First, for the approach itself, because you can see our approach is it's kind of similar to the multipath. When we do the implementation, it's very similar to the things. We add some extra functionalities at the branch point. So we think our implementation follow the same idea of the multipath related work. So that's why we think we can use our implementation, use their ideas to do the comparison. For the memory consumptions, this part, we read their paper. Their paper said it's over like 5 gigabytes. It's their numbers in the papers. So that's why we list the resource consumption over here. And for another related work, because it's statically configure different environments in advance. So that's why we also implement some like a system like this to do the comparison.
So it's based on your own implementation then? It's not.
Yes, it's not theirs implementation.
And so, just out of curiosity, so the approach you now have built this tool, is it something other people can play with? Are you going to keep working on it, or is it open source or anything like that?
I would definitely discuss with all the collaborators to allow it to be open source some days. But for now, probably it's not open source yet. Yeah.
Unless anybody else has a question, I would say the final one. Okay. So your project is actually relying on a couple of, a list of environmental queries that you think are normal for malware to obtain and to perform or to find out what environment they run in.
Yes.
What's your impression? How complete are you with this list of environmental checks that you cover with your project?
Yeah, that's also a very good question. Selecting all these things is based on the manual work. So this is will be arguably correct or complete. What we can say is we try our best based on our knowledge to do as complete as possible. And if our system can someday put into practice, I think more experts can help us to improve the completeness problems.
Just like approximate figure, how many different environmental checks do you currently cover?
For the referral paper, we are continuing working on these things. For now, we label over like 2,000 APIs, and the environments we were including over like 3,000 different environments.
Okay. Thank you very much.
Thank you.